In this paper, we present high-frequency stereo matching network. In the field of binocular stereo matching, remarkable progress has been made by iterative methods. However, most of these methods lose information during the iterative process, making it difficult to generate more detailed disparity maps that take full advantage of high-frequency information. Blurry edges, thin object missing, and textureless region mismatch are the main manifestations. Our goal is to build a highly accurate stereo matching network that recovers subtle details and preserves sharp edges through taking full advantage of high-frequency information. Our model is robust to reflective surfaces and challenging lighting conditions. The light source is moving randomly and the flashlight on the rotating table is glowing. Our model is also robust to translucent regions and handles weak texture regions well. To preserve high-frequency information, we believe that there can be three aspects of improvement. The first is to retrieve the lost high-frequency information during the final refinement process. The second is to keep the high-frequency information as much as possible during the iterative process of the network. Finally, the feature extractor may already be a bottleneck, so it is also effective to propose a better feature extractor. We designed an end-to-end network consisting of three sequentially arranged modules. The rectified image pairs are passed into the channel attention transformer feature extractor, which is capable of long-range pixel modeling, and the features are processed by the subsequent multi-scale decouple LSTM network, which could carry more semantic information across iterations. The refinement module upsamples the disparity map and perform disparity normalization before it is processed by the feed-forward structure, which could alleviate the problem of domain gap. Let's introduce our decouple mechanism. In the original GRU structure used by most iterative vision networks, the hidden state H is used to generate the update matrix of disparities, which is output of the GRU cell, while the H is also the hidden state of the GRU network, which transfers information to the next iteration. This coupling issue is proved to have a significant impact on the network performance in our ablation experiments. The process of iteration is actually the process of applying filters to the features. In the process of filtering, there is a loss in high-frequency information. Since the loss function of the network only supervises the disparity map, the output of disparity head is affected by the loss function, which then influences the hidden state H through the gradient. In this case, the hidden state H contains information that is more useful for generating the update matrix of the disparity map than passing effective information to the next iteration. We address this problem by introducing an extra hidden state C, as shown in the figure. The above-mentioned hidden state H is used for generating update matrix through the disparity head, while the newly introduced hidden state C is used only for transferring information across iterations. The design decouples the update matrix and the hidden state, which can retain more effective semantic information across iterations. Ablation studies and visualizations show the effectiveness of the method. As we can see on the left, we use PCA to reduce the number of channels from 128 to 1. The hidden state C retains more features of the edges, see the red box, and more features of the thin objects, see the blue and yellow boxes. As we can see on the right, using our decouple mechanism significantly reduces the error rate. While we have observed that in the relative independent modules in fine-tuning, the output of the feature maps may be all negative due to the domain differences, and after the ReLU activation function, the feature maps all get zero values, thus causing the network to be unable to fine-tune this part of parameters, and can only pass the feature information to the subsequent modules through the skip connection. This leads to the problem that after the network is pre-trained, some modules cannot be fine-tuned well, or even encounter model failure when fine-tuning on other datasets. To address this issue, we propose the disparity normalization to unify the disparities as the proportion of disparities over the width of the image. Decouple is also used instead of ReLU. In our experiments, we have observed the synergy between our disparity normalization strategy and Decouple. From the ablation experiments, we can also see the significant performance improvement from normalization refinement, especially for the kitty dataset that needs to go through fine-tuning. In the field of binocular stereo matching, feature extraction has not been improved significantly for years, and most learning-based methods still use ResNet-like feature extractors. This type of feature extractors has become bottlenecks in the network when providing information for well-designed post-stage structures. In recent years, transformer and self-attention have proved to be effective in many vision tasks for its long-range pixel dependencies modeling ability, while its computational cost grows quadratically with the image resolution. Inspired by Restormer, we designed a multi-stage and multi-scale channel attention transformer as the feature extractor. We aim to design feature extractors that not only capture long-range pixel dependencies but also preserve as much high-frequency information as possible. To achieve the goal of sharp edges and better deal with weak texture regions, maintaining high frequency during the pipeline is of vital importance. The most intuitive way is to maintain high resolution throughout the structure, while it leads to extremely high computational cost. While downsampling by convolution with stride or using polling mechanism will inevitably result in information loss and performance degradation. To alleviate the problem, pixel on shuffle is applied to downsample the image to 1/4 the original size and expand the channels without losing any high-frequency information. Ablation studies show the effectiveness of our channel attention transformer feature extractor. Our model shows advantage in terms of accuracy and rank first on the Middlebury leaderboard. Our method distinguishes subtle details and sharp edges of thin structures such as the leaves and branches of the plants in the living room and the overlap regions of the lines on the map and the long thin structure of the metal craft. Our method is also robust on the weak texture regions and occluded regions such as the staircase. 1 pixel area of each image is marked as a corner. Real-world generalization test shows that our model is robust even in many extreme L-post regions, such as textureless, translucent, reflective, or even self-luminous. The visualization on the kitty dataset also shows that our model alleviates the problem of blurry edges, thin object missing, and textureless region mismatch. Thanks for your attention.